Good morning to all of you. Today's point examples of the electron diffusion molecules that highlights of the borons. Borons combines with the halogen to form the trihalides. Two molecules of borons react with the three molecules of halides to give the 2bx3. Here X may be the chlorine, bromine, iodine. The boron trihalides are the covalent in nature and exist as the monomeric molecules. Boron trihalide is a covalent in nature and exist as a monomeric molecules. The boron trihalide px3. Boron is the sp2 hybridized state and three boron atoms hydrogens 3b3bh bond are formed by the axial overlap of the sp2 hybridized orbitals of the borons and p orbital of halogens. Boron is the 1s2 2s2 2p1 ground state having the 2 electron in the s orbital and 1 electron in the p orbital, 2s 2p. Excited state 2s orbital having the 1 electron goes into the p orbital, that is p having the 2 electrons, that is sp2 hybridized. 3 unpaired electrons of the boron atoms react with the 3 halogen atoms and form the 3 covalent bonds. The electron donor atom like NS3, fluorine, amines, etc. form the adducts. Coordination compound bond adduct is formed. In the boron trihalide, electron density of boron atoms from Bf3 to Bi3 decreases. Lewis acid character in case of the boron Bf3 by fluids increases as follows. Means the Bf3 get less than the BCl3 less than the Br3 less than the Bi3. Means as the atomic size increases of the fluorine atoms, Lewis acid character is also increases. But it's the reverse in case of the Lewis base. Next is the hydrides of boron. Hydrides of boron are sometimes called as the boranes. It can be classified into two series. Hn+4 called as the nidoboranes, Bn+6 called as the arachnoboranes. Simplest hydrides of the boron is the diborane B2S6. It is prepared industrial scales as the Bf3 2 gaseous 6 lithium hydride solid 450 Kelvin B2S6 gas plus 6 LiF. In the laboratory, it can be prepared as 2NaBH4 plus I2 B2S6 2NaI plus S2. Hydrides are covalent compounds and are also called as the boranes by the analogy with alkanes. Boranes have been grouped into the two classes. Structure of diboranes B2S6. Electron diffraction data suggests the following bridge structure for the diboranes. That is boron, hydrogen, boron, hydrogen, boron, hydrogen. In this case, two bond angles are there, like 120 angle boron, hydrogen, borons, clear cut covalent bonds. In case 97 degrees centigrade bond angles are also the point 30 nanometers. Bond length is the 0 to 30 nanometer structure of the diboranes. From the figures, there are 4 terminals hydrogen atoms attached to the boron atoms which are coplanar. Remaining two hydrogen atoms are involved in the formation of the boron hydrogen bonds. The bond or the bridge in case of the boron hydrogen boron, hence the hydrogen atoms called as bridge hydrogen atoms. These two hydrogen atoms lies perpendicular to the plane of the molecules and prevent the rotations between the boron atoms. Structure is satisfied by the methylations. Hydrogen atoms are successively replaced by CH3 group forming the B2S6, B2S2, CH3 by 4. Further methylation it breaks into the BCH3 by 3. This clearly explains that the four hydrogen atoms are attached to the boron atoms same type, whereas the remaining two hydrogen atoms on the replacing the molecule get the rupture. Bonding in diborans. Boron undergo sp3 hybridization in the B2S6 form the four hydrides of the same energy orbitals. P5 1s2 2s2 2p1 ground state electronic configurations having the 2 electron in the s orbitals, 1 electron in the p orbitals. In the excited state, that electron goes into the higher state, that is sp3 hybridize. 3 orbitals have the electrons, 4th orbital is empty, 2 orbitals with an electron overlap in the two hydrogen atoms form the 2 bonds. 2 BH2 units of forms are interlinked through the boron hydrogen boron bridge. Bridge formation involve the overlappings of the orbitals with the electrons of the boron on one sides and the empty orbitals of the other borons on the other sides with the 1s orbitals of the hydrogen atoms. 3 orbitals overlap with each orbital other, but only 2 electrons are available for bonding. It is the 2 electron 3 centered bondings in the boron hydrogen boron. Due to its shape, it is called as banana bonds. The formation of the banana bonds is the structures 3 center 2 electron boron bondings. Banana bonds 3 center 2 electrons boron bondings. Structure of the tetraborans. In the B4H10 molecules, total number of valence electron available for bonding is the 4 into 3 plus 12 is 22. Boron undergoes the sp3 hybridizations. Here is the electronic configuration for the borons B5 1s2 2s2 2p1. 2s electrons, ground state electronic configurations and excited state electronic configurations. Structure of tetraboron is here the borons B4H10, 6 terminal 2 electron 2 center boron hydrogen bonds, 2 electron 1 terminal 2 electron 2 center boron boron bonds, 4 bridge 2 electron 3 center boron hydrogen boron, 4 bridge 4 electron 3 centers boron hydrogen boron bonds, 4 into 2 8 electron 22 electrons. On the basis of the Williams-Combs structure is the this structure explain the how the banana bonds are formed and how the 2 center 3 electrons. Explain the formation of the p-pi back bonding in the BF3 molecules. 2p orbitals of the fluorine atoms having the lone pair overlaps lie sideways with the empty 2p orbitals of the boron atoms. Give rise to additional fluorine borons bond formed, which is the result of the p-pi back bondings. Boron fluorine boron fluorine boron fluorine give the pi bond. As a result of this donation, the electron deficiency of the boron atom gets compensated and its Lewis acid character decreases. The tendency for the back donation is maximum in case of the fluorine due to its small size. Boron's hydrogens bond explain the formation of p-pi back bonding in BF3 molecules. 2p orbital of fluorine atoms having the lone pair overlap sideways with the empty 2p orbitals of the boron atoms give rise to additional fluorine borons bond formed, which is the result of p-pi back bondings. Fluorine boron bonds pi bonding. As a result of these donations, the electron deficiency of boron atom gets compensated and its Lewis acid character decreases. The tendency for back donation is maximum in case of the fluorine due to its small size and more interaction between the 2p and 2p orbitals, hence it is least acidic. The strength of Lewis acid is the BF3 less than the BCl3 less than the BBr3 less than the Bi3. Application of BF3. BF3 used as a Lewis acid in chemical reactions. It can be used as a catalyst. And it is the different, hence used as a pair acceptor for the coordination covalent bond. Next is the structure of the BF3. Classification. Next point is the classification of the silicon. Silicon's carbon family, 14 group elements. C4Si4 elements of this silicon is the carbon family members. Elements of these groups are: the first member is the carbon, next is the silicon, then next is germanium, then next is tin, and then next is the lead. The atomic number of the carbon is a 6, atomic number of silicon is the 14, atomic number of the germanium is the 32, and the atomic number of tin is 50, and atomic number of PP lead is 82. Valence electron is the 4 and bond form is the 4. The chemistry of silicon and germanium are given here. Next is the introductions of these compounds. Group 14 elements are the carbon, silicon, germanium, tin, lead. Out of its, germanium is the rare elements. Carbon and silicon are the most abundant element by weight in the earth crust, and germanium is the only found as the traces in some silver and zinc ores. Next is the electronic configurations. The atomic carbon's atomic number 6 electronic configuration is the 1s2, 2s2, 2p2. Atomic silicon 14 electronic configuration is the 1s2, 2s2, 2p6, 3s2, 3p2. Next, germanium 32 electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. Next, the Ascent 50 electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5d10, 5p2. The valence shell p orbitals having the only 2 electrons in all the above cases. Last electronic configuration, most important, that is lead Pb 82 electronic configuration is the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5d10, 4d10s, 5p6, 6s2, 6, 4p14, 5d10, 6p2. From the electronic configuration, it is clear that these elements have the 4 electron in their outermost shells. That is, they have the 4 electron in s2 and p2. This is all about the electronic configurations of the compounds. In all above electronic configurations, one thing is common, that in carbon that is 2p2, in the silicon that is 3p2, germanium 4p2, tin 5p2, and lead 6p2. Means so valential electronic configurations having the 2 electron in the valence shell, and means the for the formation of the bondings there is 2 electrons from the p orbitals and 2 electrons from the s orbitals, means the 4 electrons. So in case bond form, there 4 electron available for the bonding also. So remaining part we will discuss in the next lecture. Thank you.